Welcome back to my YouTube channel. If today is your first day of visiting this channel, welcome. Today we are going to look at NECO 2024 Physics Practical on Electricity. We were asked to provide the following: 2-volt accumulator or two 1.5 volt dry cell. So I want to use this, each is 1.5, 1.5, that's 3. We're asked to provide jockey, 2 ohms resistor, switch, voltmeter 0 to 3, connecting wires. Then I will use this for measuring this length of Constantine wire. We're asked to provide Constantine wire of SWG, that's standard wire. So it will be written on the body if you buy a new one. But before the practical, I want to show you how I want to manipulate the readings without doing the practicals. So let's go straight into how we can, without touching any of this, still get a result, plot our graph from the knowledge of theory. I want us to use the knowledge of the theory that resistivity is equal to RA over L. Let's use what we know to get something we can work with to manipulate the readings and get something as if we did the practicals. From this, we can have it that let A come over, we'll have it that resistivity over the area is equal to R over L. That means we are getting the resistance per unit length. It means that if we know the resistivity of this Constantine wire, this is for resistivity. That is the resistivity. If we know the resistivity of the wire we are using, of the Constantine wire, and we know the cross-sectional area, of this same wire, we'll be able to get this resistance per unit length, then put it into formula to solve some problems and get. We will also employ V is equal to IR. We'll get the voltage for each length, then the resistance for each length. I is the current. So with this, we are going to get value. Remember that the Constantine wire we are using is that of SWG 26. For a wire of SWG 26, the diameter is 0.457 millimeter. The diameter of the wire is 0.457 millimeter. 0.457 millimeter. Then let's get the cross-sectional area. Since this is the diameter, let's get the radius. The radius will be the diameter over 2, which is 0.457 millimeters divided by 2. So we can end up having the radius as 0.2285 millimeters. So we can just say radius is 0.2285 times 10 raised to power minus 3. That's what I've converted this to meter. So we have the radius. And remember that cross-sectional, we are using area to be pi r square. That will give us pi is 3.142 times our r is 0.2285 times 10 raised to the power minus 3 all squared. At the end, we are going to get the area of this 26 SWG Constantine wire as 1.64 times 10 raised to the power minus 7 meter square. So we have gotten the area. Then another thing we need to get is the resistivity. Of this wire. Okay, if you check, if you Google online, you're going to get the resistivity of Constantine wire as resistivity of this Constantine wire is equal to 49 times 10 times 10 raised to the power minus 8. 49 times 10 raised to the power minus 8 ohm meter. Remember, what we want to do is to use this R to use resistivity is equal to RA over L. That's what we want to use. Where resistivity over area will give us R over L. So let's impute everything. We are going to have 49 times 10, that's resistivity over area, all over the cross-sectional area, which is 1.64 times 10 raised to the power minus 7. Okay? At the end, we are going to have 0.299 ohm per meter. 0.299 ohm per meter. So we have gotten the resistance per unit length of any given wire. Remember, we were able to get that the resistance per unit length of the wire, we got it as 0.299 ohm per meter. It means that the resistance for any given length, say 40, 50, 60, 70, 80, we are going to use 0.299 and multiply the length of that. Then make sure that you convert the length to meters. That means we are going to fill up this to get the resistance using this 0.299 times this length in meters. Then for this one, we'll get the current and fill up this. Then we'll get the voltage as well. Remember that for the voltage, during the practicals, we are going to read it off from the voltmeter. The experiment is in such a way that for each length, we'll get the potential difference. That's this and this. But because we want to manipulate the readings, that is why we are looking for I and R, so that we can get the readings we are supposed to get from the voltmeter. Okay, for the first one, we are going to do R for 40. So for R for 40, we are going to say 40 divided by 100, which is 0.4 times 0.299. That will give us 0.4 times 0.299. That will give us 0.12. 0.12. So here we are going to write 0.12. So we will do the same for 50. For R50, we'll have 0.5, that's converting it to meters, times 0.299 The same way we'll get 0.5. That will give us 0.15. So we'll have this place to be 0.15. For R60, we'll do the same thing. 0.6 times 0.299. So we can get 0.18. 0.18. For R70, we'll do 0.7 times 0.299, and we are going to have 0.21. 0.21. Then for R80, we use 0.8 times 0.299. Then we are going to get 0.24. 0.24. So with this, we have gotten the resistance. For us to fill up this current for each length 40, 50, 60, 70, 80. And in this case, we are considering that the current is equal to total voltage over the total resistance. Then we'll take the total voltage. Remember, we are using 3 volts. 3 volts. You can use 2.95. It depends on the reading instrument of the voltmeter you used initially. Okay, but we'll use 3 volts. Then we'll use 2 ohms all over. The total resistance will be 2 ohms plus RL for each length. This 2 ohms is from the 2 ohm resistor we were asked to provide. So we are taking it that is connected in series, so that the total resistance, in some cases you can have it connected in parallel. There's how to also do that manipulation, but for this one, let's say it's connected in series. So we'll say 2 ohms plus RL. So we are going to do it for the first one, where for the 40 we are going to have 3 over 2 plus the R40 that we got, which is 0. Remember, R40 is 0.12. So if we put it, we are going to have the current to be 1.42. So we'll fill up for this current when the length is 40. We'll have it to be 1.42. Okay. For 50, we'll have 3 over 2 plus RL when it's 50, which is 0.15. So that we'll get the current to be 1.40. So we'll have here to be 1.40. We'll repeat for R60, 3 over 2 plus, remember we have here 0.18. 0.18. That will give us 1.38. 1.38. We'll do for I70. 2 plus 0.21. R70 will give us 1.36. So we'll fill up 1.36. Then for R80, 3 over 2 plus 0.24. R80 will give us 1.34. So we have 1.34. Now we have succeeded in filling up the current. Okay. So the next thing we are going to do is to find the voltage. The table of values you are expected to get in the practical is mainly for this and this. They can ask you to get 1 over V, then plot V against L, or plot 1 over V against L. So let's get the readings we are expected to get from the voltmeter. So we are going to use that V for each length is I times R for each length. Please remember to like this video and drop your comment, share the video as well. Thank you. Okay, let's continue. Now V for the 40, we are using the current for the 40, which is 1.42 times the R we got, which is 0.12. So we'll have it to be 0.17, 0.17. Then for V50, the R we got 1.40 times 0.15. So we are going to have 0.21, 0.21. For V60, we'll have 1.38 times 0.18. So we can have it to be 0.25. Please watch this video let's to the end so we can see the nature of our graph, and remember to drop your contribution. Before the exam, I will work on the practical proper. For now, let's see the manipulation before the main video. So this one we can have 1.36 times 0.21, which will give us 0.29. Then for V80, we have 1.34 times 0.24, which will give us 0.32. These are the values we have. So I'm going to fill up the voltage column. I'm going to fill up the voltage column. We have 0.17, 0.21, 0.25, 0.29, 0.32. So we are going to plot graph of change in V over change in L. That's this and this, to see the nature of the graph we are going to get. This is how our table of values should look like. We have the length 40, 50, 60, 70, 80 in cm, and then the voltages. So this is the reading we obtained from our manipulation. Let's plot it and see the nature of the graph. So we are going to plot graph of V against the length. I will also use cm in the plotting. Okay, just that the slope will now be volts per cm. Okay, this is the axis for the V in volts. Please use you can write graph for V, the voltage against the length. Okay, let me use this. Let this be the length in cm. I'll put the unit. So I'm starting from the origin. I'm starting from the origin 0. I will take for this the scale I'm going to use. I'm using 10, 20, 30, 40, 50, 60, 70, 80. Then this one I'm using, since the values are, okay, let's say 0.123. Let me use 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and so on. Okay, now when L is 40, you can write your scale out. Scale on the V axis, we use 2 cm is equal to 0.1 units, and on the L axis, we use 2 cm is equal to 10 units. So you write your scale so that you get your mark. It's 40, this is 0.17. So if you count it like that, this is 0.17, 0.18, 0.19, and the next one is 0.2. Okay, now when it's 50, for 50 we have 0.21, this is 0.2. When it's 50, this is 0.2, then 0.21 is just the next line, the next small line there. When it's 60, we have 0.25. Okay, remember here is 60, and if you trace it this way, 60 and 0.2, 21, 22, 23, 24, 25 is this one. I'll mark it. When it's 70, we have 0.29. This is 0.2. You count 2, 1, 2, 2, 2, 3 until you get to this before the last one. And then when it's 80, we have 0.32. This is 0.33132. You know that this thing is manipulation. That's why all of them are almost in the straight line. If we take it from the origin, it's as if everything is perfect because it's calculated values. If you do your experiment proper, you may not really, you have it just slightly a bit scattered around here. It may not be too straight as these ones. These ones are so straight because they are calculated values. They are gotten from manipulations of the theory. Okay, so let me get, you can see the graph passing through the origin, So we can now take the slope. The bigger the triangle, the more accurate and the more you get your mark. So I'll try and get a big triangle. To get the slope, to calculate the slope. So for this, I can say change in V over change in L. Remember this point, let's say 0.3, 0.3132, 3313233, 0.33 minus, if we have it here, that's 0.1 over, for the length, this is 80 minus this length, if we 20, 21, 22, 23, 24, 25, 26, 27, 28 until we get to the next one, 29, and then 30, just like that. So this is where we need to check. We'll have 20, 21, 22, 23, 24. Let's use 25. So if we do that, so we have 0.23 over 55 to get 0.0042 volts per cm. Please remember to hit the subscribe button, turn the bell notification so that you will not miss our videos. I'm hoping to do the practicals before Monday and post it before the exam. So this is just the manipulation to prepare us for the practical things.